This exhibit is proof of quantum mechanics. So basically in this exhibit, you can turn this knob back and forth, and this will move the magnet further and closer to the lamp. So right now, the magnet is further from the lamp, and when I turn the knob, bring it closer, you can see that the green rings are splitting in two, and they just split. Sorry, my hand's shaky. So what this is revealing to us about quantum mechanics and what is happening right now is that the light emitted by the mercury gas lamp comes from the electrons jumping between energy levels. And a magnetic field is what's splitting these energy levels into two or more slightly different levels, which we see here through the splitting. Let me try to get it again. Through the splitting of the green rings, like just then. And this phenomena is called the Zeeman effect, and it's visible evidence of the property of electrons called spin, which helped establish the field of quantum mechanics. And a really cool feature of this is that astrophysics uses the Zeeman effect to detect and measure electric fields on distant stars, such as our sun. So in this exhibit, you can slide the stick left to right, which allows this pendulum thing to move. And if you slide it forcefully, sometimes, you can get the pendulum thing to go higher. And sometimes it can make its way around or balance. Or balance. This exhibit is an example of a driven pendulum, and it's called this because the system's behavior depends on the way that you vary a parameter, which in this case is the horizontal motion of the pivot point, which you vary by just moving the handle back and forth. So when this pendulum is at its lowest point, a well-timed acceleration of the base will add to the kinetic energy, which causes the pendulum to swing higher and higher if done repeatedly and rhythmically. The goal is to synchronize your hand motion with the natural frequency of the pendulum. This synchronization is called resonance, and if the timing is right, each push will add more energy to the motion. And if you pump hard enough, the pendulum can actually do a full 360 rotation, which we saw occur in the previous video, but for this to happen, the pendulum must gain enough rotational kinetic energy to overcome the gravitational potential energy at the top of the loop. And this is a classic example of energy accumulation through a non-conservative driving force, which is your hand motion. And occasionally, you may notice, like you did in the previous video, that the pendulum appears to balance straight up for a moment, and this is related to a phenomenon called the Kapitsa pendulum, where rapid vibrations or movement at the base can momentarily stabilize an otherwise unstable position, which is at the top of the swing. And this happens because the fast motion averages out the torque from gravity, which averages the torque out from gravity. However, this position is very delicate, and it requires the right combination of frequency and amplitude of your base motion. And the pendulum's behavior in the setup is nonlinear, which means that small changes in input can have big, sometimes unpredictable effects, and the system can exhibit chaotic behavior when the amplitude is high or your movements are irregular. And this is why sometimes the pendulum is flipping around, and other times it swings wildly, and it occasionally locks into a surprisingly steady pattern. And this setup demonstrates important principles that are also seen in clocks, metronomes, engineering systems.
Okay, go ahead.
Okay, so in this experiment, we will have a magnet that produces a magnetic field. Once you press this button, and then if you start flipping the coil, then the coil will begin to circle by itself. Okay, so what is happening in this exhibit in terms of physics? First, there is a magnetic field coming from the magnet. The magnet beneath the coil is producing a magnetic field, which is called B. And we can see that the magnetic field lines in this example are uniform and vertical. Second, there is an electric current in the coil. The magnetic field creates an electric current I through the wire loop, And the while loop is symmetrical, with the current flowing one direction on the left side of the loop and the opposite direction on the right side of the loop. This is because the current flows in a closed loop, so on opposite sides of the loop, the current must flow in opposite directions. And then there is, which is the key part of the exhibit, the Lorentz force, which is a magnetic force on a current-carrying wire. The key idea is that a current-carrying wire in a magnetic field feels a force, and the force on a segment of the wire is given by the equation F is equal to I dot L cross B, where I is the current, L is the vector length of a wire segment, and B is the magnetic field, and then F is the force experienced by the wire. And this force is perpendicular to both the wire, current direction, and the magnetic field, and can be found using the right-hand rule. Then we have to talk about the torque on the loop. So now think of the coil as having two straight vertical sides in the magnetic field. With the left side, the current's going up, the right side's current is going down. And then with a vertical magnetic field, the Lorentz force causes an upward force on one side and a downward force on the other. These two equal and opposite forces are separated by the width of the loop, so they produce a torque about the center axis of the loop, where torque is equal to R cross F, and then this torque causes the coil to rotate. The torque acts as long as the current flows and the magnetic field is present, but once the coil turns 90 degrees, the force flips directions and the torque would reverse. In real motors, a commutator flips the current direction every half turn, so the torque keeps pushing the same direction. But in simple demos like this one, it probably relies on either momentum to keep the coil spinning past the zero torque point, or a partially stripped wire design that cuts off current at just the right moment.